In section 9.5, we're going to continue talking about exponential growth and decay and look at some more complicated differential equations when we think about modeling and different applications. So first, we're going to be looking at differential equations of the form k times y minus a. In this case, a is a constant, or equivalently, ky minus ka. This is very similar to what we did in 9.4 practice video with the continuously compound interest problem. We had something very similar to this. We can see that a solution of this differential equation is going to be of the form c e to the kt, as we've had before, with the added a as well. We showed in the last video that if we think about y minus a equal to c e to the kt, if we replace the y minus a with y with y minus a, then we get this c e to the kt plus a solution if we add a to both sides. So that's how we're kind of looking at this, but we're going to do some extra stuff with this differential equation, with the solutions that we didn't do in the preceding video. So we've looked at differential equations of this form. We can think about them as building the differential equations by looking at the rates. So we're going to look at this example, think about how to build the differential equation, and then we're going to ask some questions about it. All right, so a patient is given the drug warfarin, an anticoagulant, intravenously at the rate of 0.5 milligrams per hour. Quite a lot of words there. All we're talking about is we are injecting this drug at a rate of 0.5 milligrams per hour. Warfarin is metabolized and leaves the body at the rate of about 2% per hour. We are going to find a differential equation for the quantity Q in milligrams of warfarin in the body after T hours. And we're going to set this up by looking at dq dt, that's the derivative that we're looking for, is going to be the rate in minus the rate out. We're going to think about how much is going in and how much is coming out. So first we have that it is going in intravenously at a rate of 0.5 milligrams per hour. Now that has nothing to do with a proportional rate, that's just the certain amount that comes in each time. So that's just going to be plus 0.5 in each hour. Then it leaves the body at a rate of 2% per hour. Now that is proportional. We're going to think about this as decay, exponential decay. More comes out at the beginning because there's more at the beginning, 2%, changes depending on how much is in there at the current time. So this is going to be our 0.02 for the 2% of how much is in the body at the time. We can say Q is again the quantity of warfarin in the body. So we're going to subtract off 2% of what is in the body at that time. So this is our differential equation. dq dt equals 0.5 minus 0.02 q. Now let's think about what is happening in this problem with different values of q. So if we have small values of q, then what's going to happen is the quantity is going to increase until the rate in matches the rate out. So we are constantly pumping in intravenously this drug, but it's leaving at a certain rate. And if we have a small amount of drug, like at the very, very beginning, we're going to be increasing the amount of the drug until those rates match each other. Similarly, if we have too much of the drug in the system, the quantity is going to decrease. The rate that is going to leave the body is going to be faster than the rate coming in until it matches the rate out. So either way, the Q is going to change until we get to some level point. And this is our next question. What is the value of Q such that the rate in matches the rate out? So we're just going to write this as rate in equals rate out. That's going to be 0.5 is equal to negative 0.02 Q. We're just going to think about this as positive, sorry, because we're going to subtract that rate. And if we solve for Q here, we have 0.5 divided by 0.02. That's going to give us Q is equal to 25 milligrams. And note that we could have found that 25 milligrams from the beginning when we look at our differential equation by factoring out the 0.02 Q, or 0.02, I should say. If we factor that out, we're going to get a 25 minus Q. And this is the differential equation that we have at the beginning, the kind of form that we want. And we could do something here, but there's something special about this 25, and there's something about if Q is less than 25, the rate in is going to be greater than the rate out. So we're going to try to get to that point, and vice versa if we have large quantities of Q. Let's look at a completely different kind of problem that has a similar sort of mechanic going on. And this is looking at Newton's law of heating and cooling. This is a physical law that describes how an item heats or cools when placed in room temperature, or in fact, placed into any kind of temperature. So we can think about this when a cold item is placed in a warmer room. So you have some ice cream and you put it outside of the fridge and it's in a warmer room. That item is going to increase temperature until it matches the room temperature. It's not going to get more than what the temperature is at that current environment. Similarly, if you have a hot cup of coffee and you put that into room temperature, that hot item is going to decrease temperature until it matches room temperature as well. That's the general idea of Newton's law of heating and cooling, and we can find a differential equation that describes this law. So let's let H be the temperature of an item at time t in a 70-degree Fahrenheit room. So that's representing our room temperature. Newton's law says that the rate of change of H is proportional to the temperature difference between the coffee and the room. So that's saying that dH dt is equal to a constant, that's going to be our K, times the temperature difference between the item and the room. That's going to be H minus 70. And there is our differential equation that we are dealing with. And again, we can see that when the temperature of the item is bigger than 70, the temperature is going to decrease. And when the temperature is less than 70, it is going to increase. So when H is greater than 70, we are going to have that H is decreasing. That means that dH dt is negative. And when H is less than 70, we're going to have that H is increasing. That means that dH dt is positive. But it's approaching this value of 70, and we're going to look at that idea on the next page. So in both of the last examples, there is this certain solution that all of the solutions are kind of approaching. For the drug example, we had this y equals 25, or I should say a q equals 25, or when the derivative was 0. In the heating cooling example, we had a room temperature H equals 70. So what this is representing is something called an equilibrium solution. And an equilibrium solution is a constant for all values of the independent variable. That graph is a horizontal line, and equilibrium solutions can be identified by setting the derivative of the function equal to 0. So again, we looked at our two examples. The one I want to focus on more is the heating and cooling example, because I think it makes the most sense in terms of what an equilibrium solution is. So if the temperature of the item is equal to 70 degrees, that is room temperature, the item will not heat or cool. It's just going to stay the same temperature. If we think about that as a graph, we're just going to have the temperature of the item is going to be 70 all the way out. However, if the temperature is below 70, we're going to have the value of H get closer to that. And if it's above, same kind of thing. But the equilibrium solution is that constant horizontal line that things are going to approach. There are two different kinds of equilibrium solutions we're going to have, those that are stable and those that are unstable. So we're going to look at these two different examples to show the difference between them. So first, we're going to find the equilibrium solution. And we can do that by setting the derivative equal to 0. That is, we're looking for, when the derivative is 0 always, that means that we're looking for a constant solution. So here we have dH dt equals -2 times h minus 20. This -2 is representative of k, and we have this h minus 20. If we set this derivative equal to 0, we have -2 h minus 20 equals 0. We can divide by the -2 and it's going to go away, and we get h equal 20 as our equilibrium solution. And we can see that in the graph as this horizontal line, h equals 20. And we can also see that we're going to have the solution 20 plus c e to the -2t. And if c is bigger than 0, if it's positive, the solutions are going to approach that line from above. And if it's less than that, or less than 0, we're going to approach it from below. But all the solutions are going closer and closer to that h equals 20. So that's what we see as a stable solution, as opposed to an unstable solution we'll look at the next page. So again, if all the other solutions, we can just look at a couple, and if they're all kind of approaching that equilibrium solution, and that's known as what a stable solution is. And I think we can use the idea of heating and cooling as a nice example to kind of latch on to understand how that would work. If you leave any kind of item out in room temperature, the temperature is going to slowly approach, or maybe quickly approach, room temperature there. On the other side, we have an unstable solution. This is something we can see in the picture here. Let's look at the differential equation. dB dt equals 2 times b minus 10. So here again, we're going to set the derivative equal to 0 to find the equilibrium solution. Divide by 2, that doesn't change anything, and we have b equals 10. Note that this k value is 2, and we could find the solution here is b equals 10 plus c e to the 2t. So here, our equilibrium solution is the constant line, but all the other solutions here are actually going away from the line as t increases. And this is what's known as an unstable solution. The best way that I like to think about this is having to do with population. If we think about the birth rate is equal to the death rate, then the population is going to stay the same forever. But if the birth rate's a little bit more than the death rate, then it's going to slowly go away from that value, and it's going to increase exponentially. And same if the birth rate is less than the death rate. They're not going to approach the same value. They're going to be kind of going off in opposite directions. If the death rate's more than the birth rate, eventually you're going to die out that population. So two different things that can go on with equilibrium solutions, stable versus unstable. There are some more sophisticated ways we can find stable and unstable, but for us, it's going to come down to we can find equilibrium solutions fairly quickly, and then we can determine if they're stable or unstable by just graphing a couple of other solutions. Look at a couple different C values and see if those lines are approaching that constant line or going away from them. Look at some more practice examples in the next video.